So in today's video lecture, we'll be talking about the noise margin of a CMOS inverter. And by noise margin, what we mean is the noise immunity of an inverter, the characteristics by which an inverter can sustain a certain amount of noise. For this video lecture, we will be covering this section from the textbook by Marilyn Wolfe. Alright, so let's start by looking at the voltage transfer curve that we have previously derived for an inverter. Now for that inverter, the threshold voltage for the N MOSFET and the P MOSFET were both equal to 1 volts. So in that case, we have seen that as long as the input is from between the 0 volt and the threshold voltage of the N MOSFET, which was 1 volt, the output voltage is VDD, and as long as the input voltage is between VDD minus the threshold voltage of the P-type MOSFET, which is equal to 4 minus 1 equals to 3 volts, and VDD, which is 4 volts. In other words, as long as the input is between 3 volts and the 4 volts, the output is 0. Now, clearly what you can see is that as long as the input voltage is 0, when the input voltage is 0, which corresponds to a logic level 0, the output will be VDD, which corresponds to a logic level 1. And similarly, when the input voltage is VDD, which corresponds to a logic level 1, the output voltage will be 0, which corresponds to a logic level of 0. Now, it is interesting. Think about the case where the input voltage is not 0. Say it's 0.5 volts or 0.4 volts or something like 0.7 volts. In all these cases, the output voltage will still be VDD. What does it mean? It means that if for some reason the input becomes larger than 0, but to some extent, when it's supposed to be 0 volts, which corresponds to a logic level 0, the output will still be VDD, which corresponds to a logic level 1. So that means that if the input voltage is non-zero, it's slightly larger than 0, when it's supposed to be 0 or when it's supposed to be a logic level 0, the inverter actually gives you the correct output, which is equal to VDD. Similarly, when the input is supposed to be VDD, but for some reason it's not VDD, rather it's equal to say 3.5 volts or 3.2 volts or 3.75 volts. Basically, when it's supposed to be logic level 1, but the input voltage is for some reason smaller than VDD, even in that case, the output will be equal to a logic level voltage level 0, which corresponds to a logic level 0. In other words, even in the presence of some fluctuation in the input voltage, the inverter will operate correctly. Now, why would the input be not equals to 0 when it's supposed to be 0 or when it's supposed to be logic level 0? It's because there might be some unwanted noise in the input of the inverter. Similarly, why would the input be smaller than VDD when it's supposed to be equal to VDD? Meaning that why should the voltage level at the input be different from VDD when it's supposed to be a logic level 1? The reason is that there can be some noise in the circuit, and essentially what this voltage transfer curve, the shape of the transfer curve tells you is that the effect of fluctuation or noise in the input of an inverter can be nullified by the action of an inverter to a certain extent. And what noise margin does is it basically tells you to what extent these fluctuations can be nullified in an inverter. It's basically a measure of the efficacy of an inverter in nullifying the fluctuations. So to get a deeper understanding, let's look at two important points in the inverter voltage transfer curve. So the first point is this one, and this at this point the slope is -1, and what the slope is defined as, as dVRO over dVi, basically rate of change in output voltage as a function of input voltage. And at this point this slope is -1, also at this point over here the slope is -1. All right, so first this point, at this point the input voltage is VIL and the output voltage is VOL. Now you can see clearly that as long as the input voltage is between 0 and VIL, the output voltage is in between VOH and VDD. And by clearly looking at this, inverter, you can clearly see that a much larger variation in the input voltage is translated into a much smaller variation in the output voltage. And this essentially again says that the effect of the noise is nullified by the action of the inverter. Similarly, at this point over here, the input voltage is VIH and the output voltage is VOL. And again, as long as the input voltage is between VIH and VDD, the output voltage will be in between 0 and VOL. Again, the shape of the inverter curves makes sure that a much larger variation of the input voltage, when it's supposed to be equal to VDD, is translated into a much smaller change in the output voltage. So essentially what we would like to do is that we'd like to make sure in an to make sure that an inverter characteristics works properly, we would say that in the output of an inverter we can tolerate this much of change of the output voltage when it's supposed to show an output logic level of 1, and it can tolerate this much of variation in the output voltage when it's supposed to give you a logic level 0. And again, another way of saying it is that an input variation in the input between 0 to VIL will give rise to a variation of this much in the output characteristics, which is tolerable. In other words, you can, in an inverter input voltage, you can tolerate a variation of this much to make sure that output voltage variation is given by VDD minus VOH. And similarly, you can tolerate a variation of this much in the input voltage when it's supposed to represent a logic level 1, because in that case the variation of output voltage is between 0 volt and VOH, which you can tolerate. And what noise margin tells you is that is equal to the maximum amount of noise that an inverter can withstand, or the amount of noise in the presence of which the inverter will still give you a correct output. And the fact that a much larger variation of input is translated into a much smaller variation in the output is called the saturating logic or restoring logic property of an inverter. Alright, so what does IL, OL, IH, OH means? So IL means input low, which is this one. IH means input high, which is this voltage. OL means output low, which is the output voltage corresponding to an input high, and OH is the output high, which corresponds to an input of IL, which is input low. Alright. So basically noise margin is defined. There are two noise margins usually defined in an inverter. The first noise margin is called noise margin low, and this is defined as the difference between VIL and VOL. So VIL is this one and VOL is this one, and the difference between them is called noise margin low, and another noise margin defined as noise margin high, which is the difference between VOH and VIH, basically the difference between this one here and the other one over here. So now let's try to understand why the noise margins are defined like this. All right. So let's consider two inverters that are connected. So the output of the first inverter is the input to the second inverter, and in between we say that there is somehow some noise is introduced. We'll just say that a noise is introduced. We'll not think about how this was introduced. All right. So let's consider the worst case scenario. So say the output of this inverter is supposed to be a logic level 0, but for some reason this output is not logic level, it's logic level 0, but its voltage level is not 0, rather it's VOL. All right. So the output of this inverter is VOL voltage, and there is this Vn amount of noise that is added here. So the total output, the value of the voltage that is input to this inverter will be VOL plus Vn. All right. So the input is VOL plus Vn to this inverter. Now again, what we have said is that to make sure this inverter operates properly, this V input to this inverter should be smaller than VIL. So what we need to make sure is that V, for this inverter to operate correctly, VOL plus Vn should be smaller than VIL, or we can say that the value of Vn, which is the noise voltage, should be smaller than or equal to VIL minus VOL. So essentially this relation means that the maximum amount of noise that you might have injected into this system, still the inverters will operate properly, is VIL minus VOL, and this is the noise margin low. And similarly you can say that when the logic level is supposed to be 1, then you can also do the same analysis, and then you can say that the noise margin that the inverter can sustain, the maximum magnitude of the noise that it can support without the inverter failing, is VOH minus VIH. Okay. So that actually brings us to a very interesting point about how the voltage levels for a corresponding logic level can be defined. Now previously what we were saying is that logic level 0 means voltage 0, logic level 1 means voltage of VDD, but actually this analysis shows that as long as your voltage is between 0 volts and VIL, the entire range of voltage you can consider it to be a logic level 0. And similarly, as long as the entire voltage range between VIH and VDD, this voltage range you can call it as a logic level 1. And this in between range between VIH and VIL, this is an undefined region of logic level, and by no means in a circuit you would want the voltage in a steady state to go into this undefined range, and this is a logic level X. X means that undefined or undetermined. All right. Okay, so now let's look at one important characteristics of a voltage transfer current, that is the symmetry. Now in the exercise that we did in the one of the previous lectures is that we took both of the inverters to have a threshold voltage of 1 volts, and also there was another characteristic that both the N MOSFET and P MOSFET had the same strength, made sure that that the threshold voltage, so the curve looks like this, and an important point was that it was symmetric with respect to VDD over 2. So when the input is VDD over 2, which is 2 volts, the output voltage is also VDD over 2, which is 2 volts. Okay. So now think about the case when your threshold voltage of the N MOSFET and the P MOSFET are not equal. And in that case, you will actually see that the voltage transfer curve shifts to the right. And why is that? Because when we were doing the analysis, we were saying that as long as the input voltage is smaller than the threshold voltage of the N MOSFET, the output will be equal to VDD. So now you need to go back and look at that analysis to understand what I mean. But essentially what it's saying is that, for example, in this the numbers that are written in red, if the input voltage is 1.5 volts, which is, if the input voltage is smaller than 1.5 volts for this case, which is written in red, so if the input voltage is smaller than 1.5 volts, the N MOSFET will be off, and as a result the output voltage will be equal to VDD. And similarly, when the input voltage is between VDD minus 0.5 volts, which is the threshold voltage of P-type MOSFET, basically 3.5 volts and 4 volts, the P MOSFET will be off, and as a result the output voltage will be 0. And if you just compare the case when the threshold voltages were, both of them were 1 volts, if you just compare the voltage transfer curve for two cases, you will see that the red curve, the voltage transfer curve for 1.5 volt N MOSFET threshold voltage and 0.5 volt P-type MOSFET, the voltage transfer curve will be shifting to the right. So that's an important property of the voltage transfer curve. If the threshold voltages are not equal while their strengths are the same, then the voltage transfer curves are not symmetric with respect to VDD over 2. And you can do another analysis where the threshold voltage of the N MOSFET is 0.5 volts and the P-type MOSFET is 1.5 volt, and you will see that the new voltage transfer curve will shift to the left. All right. So one way of characterizing an inverter voltage transfer characteristics is by something that is called a middle voltage, by a parameter called middle voltage. And middle voltage is basically defined as the value of the input voltage for which the output voltage is also equal to the input voltage. So for example, in this case where the threshold voltages of both 1 volt and 2 volts of N MOSFET and P MOSFETs were both equal to 1 volt, the middle voltage is equal to VDD over 2, which is equal to 2 volts, because when the input is 2 volts, the output voltage is also 2 volts. So again, middle voltage is defined as the voltage for which the input voltage is equal to the output voltage, and this is for this particular voltage transfer curve that we previously worked out in the class. It's a symmetric voltage transfer curve, and for which the middle voltage will be equal to 2 volts, which is equal to VDD over 2. Now in the other case that we have seen, where the threshold voltage of the N MOSFET is 1.5 volts and the P MOSFET is 0.5 volts, the voltage transfer curve shifts to the right, and in this case the middle voltage will not be equal to VDD over 2. It will be larger than VDD over 2, because for a voltage larger than 2 volts, the input voltage and output voltage become equal. So again, if the N MOSFET threshold voltage is larger than the P MOSFET threshold voltage, it will shift to the right and the middle voltage will become larger than VDD over 2. And similarly, if the threshold voltage of N MOSFET is smaller than that of the P MOSFET, then the curve will shift to the left of the black curve, and as a result the middle voltage will be smaller than VDD over 2 or smaller than 2 volts in this particular case. Alright, so let's now look at a quantitative an equation for the middle voltage. So we will try to find an expression, mathematical expression for this middle voltage here. And for that, the first thing that we write is that at the middle voltage, the input voltage is equal to the output voltage, and that is equal to the middle voltage. All right. So one important thing is that at any situation, the current flowing through the N MOSFET is equal to the current flowing through the P MOSFET. All right. So okay. So first, let's write down the equation for the current for the N MOSFET, which is equal to IDN. And if you remember that when we are in the transition region of the voltage transfer curve, specifically in the middle of it, both of the N MOSFET and P MOSFET are in the saturation region. So I'd request you to go back to one of the previous lectures where we actually studied this. Well, we did the load line analysis. That's when we found out that at this particular case of 2 volts in the in between middle region, the both of the N MOSFET and P MOSFET are actually in saturation. And for saturation, the current is given by IDN equals to half of beta N. So beta N here is simply mu N Cox Wn over Ln, and IDN is beta N multiplied with VGS minus VTN, and VGS is this much, VGSN. So when VGSN is equals to VI, which is equal to VM minus VTN squared. And similarly for the p-type MOSFET, IDP is equal to, so let's define beta P as mu P Cox WP over LP, and this is simply equal to half of beta P multiplied with, so in that case the voltage will be VSGP. So VSGP is this voltage, the voltage between the source and the gate of the p-type MOSFET. So let's write it down, VSGP, and plus the threshold voltage. And this is a little bit different from how we write the N MOSFET, because N MOSFET we write VGS minus VTN. For P MOSFET we would write VGS, we would write VSG plus VTP. Here note that VTP is a negative number. And what is VSGP? VSGP is simply the source voltage, which is VDD, minus the gate voltage, which is equal to VM, plus VTP. So that's the equation for the p-type MOSFET drain current. Alright, so as we have said, in all cases IDN equals IDP, which means that beta N VM minus VTN squared equal to beta P multiplied with VDD minus VM plus VTP squared. And if we do some more math, we'll see VM minus VTP equals square root of beta P over beta N multiplied with VDD minus VM plus VTP. Then changing signs, what we would get is VM 1 plus square root of beta P over beta N equal to square root of beta P over beta N multiplied with VDD plus VTP, and finally what we would get is Vm equal to beta P over beta N multiplied with VDD. Now what we can do is, because VTP is a negative number, we can just replace VTP as minus of the magnitude of VTP. Yeah, so there was one VTN here, so we'll just add VTN over 1 plus beta P over beta N. So this is the expression for Vm. So this slide summarizes all the calculations that we have done in the previous slide, and this is the expression for Vm that we have derived. All right. So let's first consider the case where your beta P is equal to beta N, and this is what we have actually used when we derived the voltage transfer curve in one of the previous classes, where VTN is equal to VTP equals to 1 volts, and in that case we also assumed that beta Pn is equal to beta N, and that also means that both the N MOSFET and P MOSFET have the same strength. All right, so let's first consider the case when your VTN equals to VTP equal to 1 volt, and then you will clearly see that the Vm equals to simply 1 multiplied by 4 minus 1 plus 1 divided by 1 plus 1 equals what? Equals 3 plus 1 over 2, which is 2 volts. And again, that simply says that if the VTN is equal to VTP and beta N is equal to beta P, your middle voltage will be 2 volt, which is basically this point over here, and that means that if the input is 2 volts, the output will also be 2 volts, and which will be equal to VDD over 2. So this is VDD over 2. All right. Okay, so now let's look at the second case when your VTN is equal to 1 volt, 1.5 volt, and your VTP equals to 0.5 volts. And now in this case, what you can see is that this Vm becomes 4 minus 1.5 plus 0.5 over 1 plus 1, which is how much? 2.5 plus 0.5 is equals to 3 volts over 2. Okay, sorry, I have done a mistake. So this should have been 4 volts minus 0.5 volts plus 1.5 volts. So this should have been 5 volts over 2, so which is basically 2.5 volts. And this essentially means that your Vm will actually be larger than VDD over 2. And again, this is the case that we have seen here. So your Vm is here 2.5 volts, and for an input of 2.5 volts, the output will be 2.5 volts. This is this point over here. And similarly, you can show the same thing, that when your VTN is 0.5 and VTP is 1.5 volts, your Vm will be actually 1.5 volts, which is smaller than 2 volts, and that curve will shift to the left. Again, essentially means that when your middle voltage is 2 volts, you have a symmetric voltage transfer curve, and when your Vm is larger than VDD over 2, it's shifted to the right, and in the other case, it's when your when your VTN is smaller than VTP, then the curve is shifted to the left. All right, so now the question is, what kind of a inverter characteristics that you want? So do you want a symmetric uh, uh, voltage transfer curve with a middle voltage of VDD over 2, or do you want an voltage transfer curve that is shifted to the right or shifted to the left? Now think about the case for the red curve over here. Now you can clearly see that it has a large noise margin, large noise margin low. Why is that? Because as long as the input voltage is large, it can sustain a larger input noise when the logic level is supposed to be 0. But at this, basically it means that it has a large low noise margin. On the other hand, you can see that in this particular red curve, the noise margin high will actually be smaller. Why is that? Because it's shifted to the right, for which your VIH will be larger, and as a result, if you just look at the noise margin equations, you can clearly see that the noise margin high will be low. So basically means that in this case your noise margin low will be larger than noise margin high. On the other hand, for the black curve it is symmetric, and for the black curve your noise margin low will be equal to noise margin high. Now which one would you prefer? Prefer the case where the noise margin low and noise margin high are equal, or one is in the other case where one is larger or smaller than the other one? Now you would by all means want to have a symmetric curve, in other words, in which case your noise margin low and noise margin are high, because if your noise margin low is larger, although it can sustain a higher higher noise when the input is supposed to be logic level 0, it can sustain a much smaller noise when the output voltage is supposed to be logic level, input level is supposed to be logic level 1. And in an inverter you would expect zeros and ones to come with the same probability. So you would actually want the inverter to have same amount of immunity with respect to noise in logic levels, input logic level 0 and input logic level 1. And as a result, you would want to have the noise margin low to be equal to the noise margin level of high. All right, and what we have seen in the analysis that we did, we have seen that if the threshold voltages are equal, then and the beta n and beta p are equal, then you would get a middle voltage of 2 volts or VDD over 2, and in that case the noise margin low will be equal to noise margin level of high. Alright, so now in the previous analysis what we have done is we have assumed that beta n is equal to beta p. But what is beta n and what is beta p? So beta n so again what we have seen is beta n is, so let me write it over here, beta n is equal to mu n Cox W n W L n, and beta p is equal to mu p and Cox Wp over Lp. Alright, so Wp over Wn is simply Wn over Wp, mu p multiplied with Wn over Ln over Wp over Lp. Okay. Now what we have also said one of the previous classes is that mu n is usually larger than mu p, and as a result, if you want to make sure that beta n is equal to beta p, then usually mu n over mu p is equal to 3. So you would get something like this. LP, and if you want WP equal beta n equal to beta p, then what you will see is that WP over LP equals to 3 of Wn over Ln. So this is what you need to make sure to have. So WP over LP should be 3 times Wn over Ln to have beta n equal to beta p. And in the previous case, when we drew this black curve, we assumed that Vtn equals to Vtp equals to 1 volts, and we also assumed that the beta n equals to beta p, and that essentially means that for this black curve, actually the W over L for the p-type MOSFET is 3 times larger than that of Wn over Ln. Now if Lp and Ln are equal, then essentially means that the p-type MOSFET is 3 times wider than the n-type MOSFET. All right. And again, if your threshold voltage of the n-type MOSFET is equal to the p-type MOSFET, you need to have the width of the p-type MOSFET 3 times larger than that of the n-type MOSFET, or the width to length ratio of the p-type MOSFET 3 times larger than the width to length ratio of the n-type MOSFET. So now let's think about a case where both of the n-type MOSFET and p-type MOSFET has the same width to length ratio, and also let's assume that the threshold voltages are equal to 1 volt. So in that case, what will be the beta n over beta p? So we have already seen this result here. So mu n over mu p is say 3 multiplied with, now we have said that for this case, so this case is Wp over Lp is equal to Wn over Ln. So these two are equal, so this will be 1, so this will be equals to 3. Alright, so let's see what will be the value of Vm. So Vm will be equal to, so beta p over beta n is basically 1 by square root of 3 multiplied with 4 minus 1 plus 1 over 1 plus square root of 3. So basically it's 1 over, so this will be 3, so it's a square root of 3 plus 1 plus 1 plus square root 1 over square root of 3. So this will simply be equal to square root of 3, which is smaller than 2, or which is smaller than, so 2 is VDD over 2. Alright, so that means that, and this middle voltage will be 3, and essentially the voltage transfer curve corresponding to W over L for the P MOSFET equal to the W over L for the N MOSFET will shift to the left with respect to the symmetric voltage transfer curve. Alright, so again this means that if the N MOSFET and P MOSFET has the same width to length ratio, the voltage transfer curve will not be symmetric, rather it will shift to the left and the middle voltage will be smaller than VDD over 2. Now what we have said previously is that we want a symmetric voltage transfer curve because that ensures that you get the maximum noise immunity for the inverter characteristics. So that means that actually to make an inverter, the width to length ratio of the p-type MOSFET should be larger than that of the width to length ratio of the n MOSFET, and it should actually be 3 times the width to length ratio of the p-type MOSFET should be 3 times larger than the width to length ratio of the p-type MOSFET, because the ratio of electron mobility and to the hole mobility is almost 3. All right, so That's an important design consideration again for inverters. Now, we have previously seen exactly same relationship when we were talking about delay. What we said was that you want the rise delay and the fall delay, or the rise transit time and the fall transit time, to be equal. And to make sure those rise transit time and fall transit times, or rise delay or fall delay, are equal, we also said that the width to length ratio of the p-type MOSFET should be equal to the width to length ratio, should be 3 times equal to the width to length ratio of the p-type MOSFET. So there are two reasons as to why you would want the p-type MOSFET to be wider than the n-type MOSFET.